what the third degree Taylor polynomial is. So notice this doesn't say the first three non-zero terms. I don't know what that degree would necessarily be, to be honest with you, at least not right now. But it does say the third degree. So I know that I'm done when my exponent on my x's is 3. Hopefully that's just a handful of terms. Probably that's going to be the case. So if I'm going to find that third degree Taylor polynomial, I'm going to start off by simply finding, or centered at 0, of course. I just need to find f of 0. So f of 0 would be sine of pi over 4, which is?
Root 2 over 2.
There's my first term. That's my 0th degree term. So I got a little ways to go still. That's my first term. And then, to find my subsequent terms, I need to start finding some derivatives. So f prime of x is going to help me find my next term. F prime of x would be 5 cosine of 5x plus pi over 4. And of course, f prime of 0 would be 5 cosine of pi over 4. Do you guys get 5 root 2 over 2? Okay. So this would be 5 root 2 over 2, technically times x minus 0. I'm just going to put times x. So far, so good? Okay, yeah?
Do we need to simplify 1 over root 2 to root 2 over 2?
Either way is fine. That doesn't matter to me. Yep. Okay, so now I've got to find my second degree term. I've got up to a first degree. So my second degree is going to be based on the second derivative. Second derivative would be negative 25 sine of 5x plus pi over 4. Again, that chain rule factor multiplying by the 5 on the outside is going to continually mess around with the positives and negatives. So I got f double prime of 0 equals negative 25 times sine of pi over 4. So I'm getting negative 25 root 2 over 2. Still making sense? Okay. So then that term would be minus 25 root 2 over 2 times x squared over 2 factorial. Or, of course, just 2 works also. Bless you. And it looks like this is going to be my last term because I'm looking for third degree and I'm up to second degree. So third degree would be third derivative. And that would be negative 125 cosine of 5x plus pi over 4. So at the centering point, this would be negative 125 times root 2 over 2. You guys all doing okay? All right, so then I put this in, negative 125 root 2 over 2 times x cubed over 3 factorial. Sorry I switched colors on you there, but that'd be my third degree. I have no idea what 125 root 2 over 2 is. Times 1 over 6. That's okay. Questions so far? We need to talk about B, but this would be our third degree. Third degree Taylor at 0 for this. Is this an alternating series?
Yes.
Alternating literally means the signs alternate, just in blocks of 1. And like I can see why you'd say kind of, because it's like plus, minus, minus, like plus, plus, minus, minus. Is that going to continue on forever? I don't think so. Yeah, it might. Yeah, it might. If it does, yeah, there will be some cycle to it because of the derivative of sine and cosine, but it's okay. So guys, any follow-ups, any questions at all? Okay. So then B says, this is what we did last time, use the Lagrange error bound. So let me ask you, why would it prescribe the Lagrange error bound? If we were going to try to find and quantify an error here, why would we use Lagrange error bound versus the alternating series error bound? Because it's not an alternating series. I mean, it really is that simple of a decision point. It's not what it is. So we've got to use this. Remember, the Lagrange error bound is a much broader tool. Like you can use it on any series, whereas the alternating series error bound can only be used on alternating series. Okay. So it says, to show that, can anyone explain what this is right here? R.
N.
The error. Yeah, that's the error. This. What is this? What is f of 1/10? Is it the? It's the what? It's the actual value. Yep. Actual value of f. And what is this? Yeah, that's the approximation. So if I have the actual value and I subtract out the approximation, that would tell me exactly how far off I am. We're wanting, so that's the error. So we're wanting to know, we're wanting to show or prove, I guess, that if I plug in a 1/10, that I would be less than 1/100th off from the actual answer. You see why that would be useful information? Like if you're supplying an approximation, that's one thing. But if you could also say, and I'm less than 1/100th off, that gives a little bit more of a better picture as to what you did and how good or bad it was. All right. So let's think this over. There's 3 parts to this. I'll write it out here for you. We'll say the error is less than or equal to, does anybody remember what comes first? It's in the numerator of a fraction. Absolute value of x minus c. So what's my x value? 1/10 minus, what's my c value? 3? 0. And we're supposed to raise this to the n plus 1th power. What's the n plus 1th power? Yeah, because we got to degree 3, so we're at n equals 3. 1 more would be 4th power. All right, all divided by 4 factorial, right? The n plus 1 factorial. And I said this last time, I think it's worth saying again. These first 2 parts, the numerator and the denominator on this fraction, they are formulas. So please don't let kind of the complexity of it confuse you. It's always going to be x minus c to the n plus 1 over n plus 1 factorial. And as long as you can get the x and the c and the n in the right spots, you're good. What comes next requires a little more, and I think it's varying degrees. I think sometimes it requires just a little bit of thought, ranging all the way to, wow, I'm not sure what to do. And you're going to have to put in a lot more thought. So there's going to be a range of thinking that needs to happen here. So what comes next is the max value of the n plus 1th derivative at z, and z is some number between 0 and 1/10. That's right. We don't know exactly what z is. Neither do we have to exactly find it every time. So we're talking about the 4th derivative, the max value of the 4th derivative. Any suggestions on what we might do? Find the 4th derivative? Fair enough. I do have the 3rd derivative. So 4th derivative, just to piggyback off what we did earlier, 4th derivative of x would be 625, wouldn't it? Positive. 625 sine of 5x plus pi over 4. Anybody find that helpful? Looking for the max value of that 4th derivative on the interval from 0 to 1/10. And I would say, I don't know if you guys see at the top here, it says 2004 BC6. That means it was free response 6. That means it's no calculator. So what you cannot do is you can't graph this on the window from 0 to 1/10 and say, look, I found it, it's right there. So I would say this is one where there's going to have to be a little bit more thought put into it. Josiah, what do you think?
I would use the max value of the 4th derivative evaluated at 1/10 because
Shh,
that's
listen.
because it's greater than the value when it's at 0.
How do you know?
Because because the sign, like if you're the sign of pi over 4 is like at 45 degrees, which is root 2 over 2 times the 625, but adding that, adding something to the pi over 4 is going to give you a bigger sign value than
Adding something to the,
adding
like the
something
5?
to the pi over 4.
Well, but if you add something to the input, doesn't it just like shift things? You know, because your normal sine curve does this, right? Adding, because we're really, like if you just think about the argument, we multiplied the inside by 5 and we added pi over 4 to get this, right? Isn't a plus on the inside a shift left?
Yes.
And doesn't the 5 take what normally was a period like this and go?
Yes.
So I mean, I honestly, Josiah, I got to be honest, I have no idea if you're right or wrong. I'm sure we could figure it out pretty easily. If you're using a calculator, that's one thing. I think we probably could figure it out even without a calculator, but I think we can do it even easier. I really do. Plug in what? All I'm really saying, Josiah, is we're talking about something really complex as far as like the graph, because you have a graph that has been changed a lot, right? It's technically been shifted left pi over 20, and its period has decreased by a factor of 5. So I think it's sort of hard to say, hey, the right edge is higher than the left edge, or the left edge is for sure higher than the right edge. Or it could be that in between there's a peak or there's a valley, right? It's hard to say without looking at a calculator, because this can and should be done without a calculator. You might be able to do it that way, but I think there's an easier way. Does that make sense? Okay. Some other thoughts? Matt?
Could you just do like, I remember like a month ago we were finding like absolute maxes, just find the critical points and the points.
Yeah, sure. So you could, if you were going to find the absolute max or min of the fourth derivative, like this fourth derivative of f, what would you need to do? Go to a fifth derivative. Yep. Set that equal to 0. And consider 0 and 1/10. And I think you're going to run into some issues, especially with the 1/10. Whatever you get, like when you try to plug in a 1/10 in that, you're going to get sine of 1/2 plus pi fourths.
That's what I was thinking.
I'd love to just like know what that was real quick, but I don't. If the calculator's active, then that starts to make sense. But the calculator's not active, so
I was really hoping that wasn't what you had to do.
no. Dylan, what do you think?
I don't know if this is right, but could it just be pi over 2?
Would the answer just be pi? What do you mean by the answer?
Would z be pi over 2?
Would z be pi over 2? Well,
because sine pi over 2.
Well, I don't think so, because pi over 2 is not between 0 and 1/10. It's got to be on the interval from 0 to 1/10. Nick, what do you think?
When you do the fifth derivative, it's positive in front, it's not negative, and then from the interval 0 to 1/10, I know that 1/10 isn't greater than, or 1/10 times 5, or not greater than pi over 4. Means if I add it to that, it won't go past pi over 2, which means sine will decrease.
Mm-hmm.
So I know that if I take that derivative, I know it's positive. I can also say it's positive from the interval 0 to 1/10.
Okay.
Unless it's the rightmost value.
I think that's pretty good reasoning. What do I do with it? What number do I plug in for the fourth derivative at z? So like z is 1/10. Okay, so then how do I quantify this? Because remember, like I think your reasoning is pretty good. I really do. But remember what we're trying to do here. It says use Lagrange error bound to show that the error is less than 1/100th. So what I can't do is just say because that's obvious. I gotta go further, right? And so I think I think where you're going to run into trouble, I think conceptually you have a good idea. I think you're going to run into trouble mechanically because the fourth derivative at 1/10, we're going to have to plug a 1/10 in there. So we're going to have to say, all right, sine of 5/10 plus pi over 4. Without a calculator, it's like through 2 over 2-ish, right? We're going to be like sort of close to root 2 over 2, but maybe, a little bit more than that, right? But we don't know exactly how much more, so we have to like prove this. And to do it without a calculator is going to be really hard to figure that number out. I think we can do this without going, you guys are going, like, it's kind of what you said, Josiah. You guys have similar ideas. You're going really detailed. And there's nothing wrong with that, except we don't have the tool to deal with your level of detail, because we don't have the calculator.
Would you just find the z value, just do what Nick was saying, find the fifth derivative, set it equal to 0, and find where it goes from positive to negative.
Good luck doing that without a calculator. It's going to be so hard. I mean, after hours and hours of working at it, we might be able to come up with a pretty decent approximation. We could even, I'm going to scare you when I say this, we could even go back to Newton's method for approximating roots. And we could make our step size like 0.00001 and write a computer program for it. But then we need a computer. Does that make sense? We're going to run into all kinds of issues without technology. Think really big and broad, and be willing to kind of take a chance on a big, broad level. Any other ideas? Like I would say, like Nick and Josiah have come up with some, I think, really, honestly, if we had a calculator, some very intelligent approaches, and we'd already be done. And no problem with that. If we had the tool to deal with that level of detail, but we don't. Johnny, what do you think?
So if it's 1/10 to the fourth, and it'd be 10, or then be like, that'd be a very small number, and then it's divided by 4 factorial as well. Could you
Yep.
somehow prove that even at, because like the highest sign could be is going to be 2, or it's going to be 1, right? The sign's always going to be within 1 and 0. So the highest is going to be 1. So the highest that max,
The highest what could be?
highest sign could ever be is 1. So then 625 times 1 is going to be the very max f to the fourth could ever be.
Okay.
So if you multiply 625 by 1/10 to the fourth over factorial of 4 factorial, we get, and if that comes below,
So I want to make sure I have this clear. So I'm going to write this out. What you're proposing is that we replace this with 625.
yeah.
What do you guys think about that? Did you hear? I mean, he presented as similar to like Nick and Josiah. He explained why he thinks that. Do you think that's reasonable? Yes? Okay. So you know what? I think just like Nick and Josiah's was reasonable conceptually, but maybe unreasonably detail-wise, this is reasonable conceptually, and it's reasonable to do detail-wise, I think, but is it going to work? That's the issue. So I want you to make sure you heard what Johnny said, because if this works, this could be great, because I think we can make this, I think we can make the numbers work here. He's basically saying the highest 625 sine of whatever could be is 625. We don't know if that's going to happen on the 0 to 1/10. It may or may not, but we don't know exactly. But we can say for sure that 625 is the most it could be. So let's explore. Let's just see how this works. Are you guys ready to put on your arithmetic hats? Because that's what we're going to need to decide if Johnny's idea actually works. So times 625. So how about this? What's 1/10 to the fourth? Can I do fractions? I do better with fractions.
1/10.
That's right. Good job. 1/10,000. 4 factorial. I think maybe I'll write 4 factorial out as 4 times 3 times 2 times 1. And what's 625 really?
625.
But it's a bunch of 5s. So how many 5s?
5 to the
Fourth, right? So 5 to the fourth. So I'll continue on over here. I hope I gave myself enough room to actually get to an ending point on this. I'm going to say that this is 1/10,000 times 4 times 3 times 2 times 1. times 5 times 5 times 5 times 5. And I'm going to start doing a little cancellation. So check this out. How about 5? Oops. I didn't want it to totally disappear. 5 would cancel with 10,000 to be what? 2,000. And wouldn't this 5 cancel with the 2,000 to be 400? Wouldn't this 5 cancel with the 400 to be 80? And then finally, this 5 would cancel with the 80 to be 16. All right, so as long as we can do 16 times 4 times 3 times 2, we're in good shape. So what's 16 times, I don't know, you could do this in all kinds of order. 16 times 4 is
64.
Times 3, 192, and times 2, 384. So this is actually equal to 1 over 384. Is that less than what we were supposed to be less than? Yeah. So, Johnny, ding, ding, ding. That's the way you got to do this.
Okay, good job, Johnny.
Yep.
Yeah, Johnny.
So, I want you guys to hear me well. It all depends on technology. Josiah and Nick's idea and Matt's idea of let's find some absolute extrema and find the fifth derivative and do it. Like, that's totally reasonable if you have the right tools for the job. We just didn't really have those tools for the job. And beside the point that on some question like this on an AP test or one of my tests, I have not allotted like 5 hours for you to do the question. Right? I mean, it'd take you a long time to get all that done without a calculator. It doesn't mean your ideas were bad. They just weren't appropriate for the tools, right? Johnny's idea is good simply because it fit within the parameters of here's the tools that we have. And thank God they didn't ask us to prove that it was less than like 1/500th. Because we wouldn't really have a good way unless we went to the level of detail as was early suggested. We wouldn't have a good way to do that. Odds are pretty good the error is less than what we've calculated the bound to be. We just don't know. Yeah, go ahead.
We can just write 625 in there without doing anything.
So the way I put it is, and we'll get in the next question, we'll get into this again a little bit. For this number right here, this number simply has to be an easily defended number. Defended as if somebody questioned you and said, why'd you put 625? It needs to be easily defended based on the tools you have available to you. Now, if we did have the calculator active and you put 625 there, I'd say you could do a lot better than that. You could just graph it on your calculator, right? The fifth derivative. It wouldn't be that hard to do.
Would they count you wrong if you do that?
No.
When there is calculator?
No. Oh, when there is calculator? Well, what they would do is they'd tighten up your error. They'd say needs to be less than 1/1000th. They would tighten it up to the point where you would have to do something a little more strategic than just, let's just pick. But based on the tools you had, can't you confidently say, and think about it like this, can't you confidently say that there's no way that the fourth derivative is bigger than 625? I can say that whether I've got a calculator or not, I can for sure say that. Can I say for sure that it's less than 400? I don't know, maybe. Can I say it's less than even 620? Probably, but I don't know for sure unless I could do some more advanced calculating. 625 is easily defended. You'll be set up for success, right? They're not going to say, wow, you used 625, but it should have been 623.8, and you didn't have the calculator, and I don't know how you're supposed to get that, but good luck. You're going to be set up for success as long as you know how to navigate this error bound. You'll be in good shape. Yeah.
Is that like the way John did it? Is that the way that you were going to?
Yes.
So that's the way that we should do it.
I don't know if it's the way you should do it. It's the only way that I can see that you can logically do it. Like if you, like let's say you decided, you know what, I'm going to put 600 right there. I'm going to come back to you and say, that's cool, Matt, because it would work out. You can tell it would work out. I would say, why did you pick 600? Like, what's your rationale for that? I can see the rationale for 625. Without a calculator, I can't see it for 600.
For 625, it's like the worst possible case.
Exactly, because the amplitude's 625.
Yeah.
So we can for sure say that that's the max that fourth derivative could be.
That would be like the biggest that the error would be.
Yeah. And based on the tools that you have, that's really the best you can do.
Yeah.
So just think, I'll go back to what I said. You want it to be a number that you can easily defend based on the tools that you have available to you. Hello. All right. So, oh yeah, Emma, go.
Do we have to justify that 625? I didn't write anything.
We did it. We did it right here. All that arithmetic of, hey, here's the Lagrange error bound, and we simplified this thing down all the way to 1/384th. And that's less, and you know, clearly that's less than 1/100th. That's all you really have to do. Yeah. Yeah, no concluding. I mean, obviously, if you do, that's okay. But you don't have to write like a concluding sentence.
So by saying that, can you just say like 620 and then justify it the same way?
Well, so the problem is more on the front end than the back end. Like, I could put in, instead of 625, I could put a 10 right there. And we all know that that would show an error less than 1/100th. The question would be on the front end of like, well, where'd you come up with 10? And are you sure that on the interval from 0 to 1/10, the max value of the fourth derivative is 10?
Yeah, but that's what I mean. Like,
It's not easily defended. Like, it needs to be a number that if somebody said, why'd you pick 10? You can't say, because it worked. That's circular reasoning. Why did you pick 10? Well, because it worked. Well, why did it work? Well, because I picked 10. If I were to say, why did you pick 625? And you said, well, sine is cyclical, and the highest or lowest it could be would be plus or minus 625, I could say, yeah, makes sense.
but that's what I mean. Like, should we say that instead of just proving it with arithmetic?
No, I'm totally okay if you just write that number in there. I mean, if you want to give me an explanation as to why, especially if you think your reasoning is a little off the wall. But there needs to be a clearly seen reason as to why you picked that number. And it needs to work if you want to prove that the error actually is less than, in this case, 1/100th. Anybody else? This is the one time when your arithmetic matters. Here's what you can't do. I think this is a good, because normally, you guys understand, normally, like if you had some question on the AP test, I'll just write this up here. You had some question on the AP test, and they're asking you to find the rate of change of something, and you said, all right, the rate of change at 2 is equal to, pi over 3 plus sine of pi over 6 minus 8. You understand you don't need to do all the arithmetic there, like you could leave that unsimplified, right? This is the one time when your simplification matters. What you can't do is you can't say, well, 1 over 10,000 times 4 factorial times 625 obviously is less than 1/100th. I mean, everyone knows that. Yeah, any kindergartner worth their salt knows this. I don't need to go any further, all that stuff. So you actually do need to go through this little, hopefully brief, arithmetic process of showing, yes, as a matter of fact, that number is less than 1/100th, and then you're good. So this is one time when you're simplifying matters. Yeah.
I was like, do we have to go all the way down to like 1 over 384, or could we have done like 1 over 16 times 12 is going to be the
Is that obvious?
Yeah.
The tone of voice tells me it's not. It's not that obvious.
It's like 12 times 12 is 144, so like 12 times 16 is 12 times. So it'll be
Two
greater
number
than
bigger than two
It's safest, I will say it's safest to just like take it to, like the most simple version. Yeah.
What if you mess up, like, let's say, like, if it's like 1 over 12 times 16.
And you mess up the
say that's,
multiplication.
like, maybe 160.
Yeah.
And what would happen? Would you get it wrong?
Well, I would, in that case, I would say it'd be a two-point question for sure. And the first point is usually like uses the Lagrange error bound correctly would be the first point, and then usually analysis is the second point. If it were me grading one of my quizzes or tests, I'd probably give you like 1.5 out of 2 and say, 16 times 12 is not whatever you said it was. AP test, you'd go 1 out of 2. They would say, hey, good job setting it up, everything looks great, but then your analysis was messed up because you flubbed the multiplication. Of course, it's not even algebra, it's more like 6th grade math or whatever. So just be careful, because we all know you can do it, but all of us still make little mistakes from time to time, so just be careful. All right, so let's move on to our final example that's similar to this. It's example number 3. And it's right here. Okay. Packaged a little bit differently.
Is this calculator?
I would say not. I would say not. So please read it over. It says fifth degree Taylor polynomial for g about x equals 0, meaning that it's really Maclaurin, is given by that equation right there. The graph of the sixth derivative of g is shown below. And then you're asked 2 questions. See if you can answer both. So A, I'll try to be really careful with my notation. I'm going to say this. G of 1 is approximately equal to P of 1. I'll put P sub 5 of 1. Make sense? And that equals, all I have to do now is plug in a 1. So P of 1 would be 1 plus 1/2 plus 1 over 72 plus 1 over 3600. It wouldn't be that hard to simplify this, but let's not bother. Just leave it alone for now. You're doing enough arithmetic as it is, more than you bargained for probably. You guys okay with that? Now, we know the centering point is 0, and we know we're evaluating or we're trying to find an approximation for g of 1, so we're off the centering point, so we know that we're off. There's an error, and so I'm going to say something like this. Absolute value of g of 1 minus p of 1. That's my error. And my error has to be less than, and I have to use the Lagrange error bound y. It's not alternating. If it was an alternating series, I just figure out what that fifth term is, like the first neglected term, and that's going to be my error bound. But it's not alternating, so I cannot do that. So it's going to be x minus c. So it'd be 1 minus 0 to the n plus 1. What's n plus 1? 6. All divided by what? 6 factorial times the max value of that sixth derivative. This is where we go back to the graph and say, you can see the high point. It's right there. Isn't that the max value? It's right there. Max value. Remember, what you have to do is you have to basically pick a value for the max value of the sixth derivative that is defendable based on what the tools and the visuals and whatever you have in front of you. What if I did this? Would you guys be okay if I said 5.634? You okay with that? Are my eyes that good? Okay, yeah, guys, actually, I did make a mistake. It should be this. I'm being ridiculous now, right? I mean, can you tell for sure that high point is less than 5.8 or 5.5 or 5.62? What can you say for sure? Less than 6. Isn't 6 for sure? We know it's probably less than that, but we can say for sure it's no higher than 6. And so what I would do is I would not put all that junk. I would just put times 6. And if somebody were to come up to me and say, well, how do you know that's the case? Maybe you could draw a little horizontal line here and say, look, that's a y value of 6, and you see how the high point is a little bit less than that? That's very easily defended. If you wanted to put 5.8, I can't even find 5.8 on the y-axis. Neither can you. All we can do is take a decent guess, and who knows if it's right or not. You got to go with 6. Okay, so I made the numbers pretty easy here for you. The numerator, of course, is just 1. Wouldn't this 6 cancel with the front 6 off the factorial? So this would really just be 5 factorial. And what's 5 factorial? 120. And that is indeed, of course, less than 1/100th. So we've proved it. We used Lagrange error bound. That 6 is a key number. And, of course, you're set up for success. I was talking with Matt earlier. Instead of a 6, do you realize that you could have put a 10 right there? Isn't that an easily defendable selection? Can't you say for sure the sixth derivative is less than 10? Yeah. You could. But you know what? I don't think that would have worked out very well as far as proving less than 1/100th. For that matter, you could have put this. I mean, can't we for sure say the sixth derivative is less than 1,000,000? but I think then your quest to prove that the error is less than 1/100th would have fallen a little short, right? You would have struggled and said, whoa, maybe I should try to cozy up a little closer to what the max actually is. Hopefully you would have arrived at 6. Question? Or is that where you're going?
Would you need to defend like your choice, or could you just say
Defend what?
like the choice of 6?
No, you really don't have to justify it. As long as it's, again, easily justifiable. And I will be picky about this. Like if you were to put, and I don't know why you would pick this because no calculator active, this would be a mess. But if you put 5.9, I'm going to look at that and say, how do you know? Like, really? How did you pick 5.9? Is it just a guess? You don't know. You do know 6, right? And so I think we could go with that. So yeah, if you go beyond the obvious and feel like you need to justify it, then you probably know what you should have picked.
Okay.
Does that make sense?
Yeah.
Okay. Colin.
Would you ever give us like the fifth derivative in a specific problem and we have to calculate the slope of matching slope?
I can't see why that couldn't happen. I don't see why somebody couldn't do that, but you'd need some more tools beyond what I just gave you here. But yeah, I mean, you could create a really awesome problem where you look at concavity and say, if I did a secant line slope and, you know, blah, blah, blah. I'm not saying it hasn't already been created. I'm just saying you could create that for sure. Okay, anybody else with a question?
So does that, like, is that enough for explaining why?
Yeah, because what we did is we started off, we created an acceptable error form, Lagrange error bound. Oh, except my 6 got erased. There we go. Now it's an acceptable error bound. Did a little arithmetic, and we proved that, yes, the error is actually less than the thing it was supposed to be less than. I think we're good. Anyone else? Okay. So this all ties in very nicely with where we're going. I want to remind you, kind of the whole point. This is like what we've been doing for the last week or so is kind of the whole point of this unit. It's the, how can I take something that's not a polynomial and represent it with a polynomial? Like that's kind of the whole thrust of this unit. And we have done this a lot, right? For like over the last week plus, we've been looking at how to do that. And each time I've said things like, you know, the polynomial is really only accurate at the centering point. The minute you move off the centering point, there's some inaccuracy. And we've been working on how do you quantify that? How do you bound that? So what we kept on saying, though, is if you just add more terms, the error gets less. Not good enough? Add more terms. Still not good enough? Add more terms, right? The question is, we keep adding more and more and more terms. We're heading towards, like, what if there was an infinite number of terms? The bigger question becomes, okay, e to the x is represented by 1 plus x squared over 2 factorial ... Is that good for all x values? Or is it like the geometric series where x has to be between -1 and 1? In other words, what's the domain for this? And that's what we're going to look at here. Hopefully you guys looked at the power series intro video. And hopefully you're okay with going back to use the ratio test, because that's all this is, mostly using the ratio test. So I thought we would do an example or two here. I think let's definitely do this one first. And I thought I would try to piggyback off the video here for you. So check this out. It says find the radius of convergence of this. First of all, let me ask you, can anybody tell right away what's the centering point for this series?
0.
How do you know?
It starts at n.
This does not indicate that the centering point is 0. What do you guys think? What do you think it is?
Like the c value is 0 because you have x. It's just x to the end, not like x plus another.
Yeah. If this was x minus 5 to the n over n factorial, it'd be centered at 5, right? If it was x plus 5 to the n, blah, 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 it'd be centered at -5. So Josiah said it quite well. Because it's just x to the n with no plus this or minus that, we know technically it's x minus 0. So it's centered at 0. The question is, all right, how far past 0 could we venture and still have a good error boundable approximation, right? Instead of just something radically wrong. So the way we do this is, of course, with the ratio test. So I'm going to set it up limit as n heads towards infinity. And what goes first in the ratio test? N plus 1. The n plus 1, whatever it is. So this would be x to the n plus 1 over n plus 1 factorial. And then I usually multiply, what do you multiply by? It's not just the nth, really, it's the reciprocal, because it's a copied out flop. So reciprocal, so n factorial over x to the n. And here's how we use the ratio test just a little bit different. We want to set this up for convergence, right? So this needs to compute to be what? Less than 1. So I'm just going to put that in here right away, because I'm not looking for the radius of divergence. I'm looking for the radius of convergence. So I'm going to set this up to be less than 1. How strong are you guys getting to be at simplifying these really complicated looking things inside there? Any ideas? Like, what do you think this and this would simplify to be?
X.
Just x, right? The n, you'd subtract n plus 1 minus n, so it would just be x to the first. And then how about the factorials? N plus 1 where? In the bottom, in the denominator, yep. Okay, so n plus 1. Doing good. Okay, so then if we did make n head towards infinity, what would be the result on the left side? 0, right? If x is some number, it really doesn't matter what number it is, right? It could be huge, could be tiny, positive, negative, fraction, whatever. You're just going to get 0. So this means 0 is less than 1. So what's the domain for this? What's the acceptable x values? All of them. That's right. Because 0 doesn't depend on x. 0's just 0, and 0 is always less than 1. So because of that, we can say that the radius of convergence is infinite. Okay? So in other words, if you just keep adding more and more terms, not only does the error get less and less and less, but the apparent radius of convergence just gets larger and larger and larger. And if we could ever head and get really close to an infinite number of terms, this would exactly represent its original function. Does anybody recognize what this is, what this power series is? It's e to the x. Yep. So this right here is equal to e to the x. So the radius of convergence for this Maclaurin power series for e to the x is infinite. If you don't like how it looks, just add more terms and it'll get better. Don't like how that looks, just add more terms. It'll keep getting better and better and better. The radius of convergence will just get wider, larger and larger and larger and larger until your calculator screen needs to be widened. And then you widen it, and then you just add more terms, and it gets better and better and better. It'll just keep widening out the more terms you add. Questions?
I was just wondering, like, because there is the situation where if it's only, say it's like when it's only when it converges only at c equals 0. So like in this case,
What would your radius be for that?
For what?
If
well,
yeah,
R
if
equals 0, so.
if your power series only converged at the centering point, what do you think your radius would be? 0. Yep.
Yeah, so that's what I'm saying. So r equals 0, but then would the c value have to be like greater than 0, or
C
or
value.
Not equal to 0.
C. I don't see a C value anywhere. Are you talking about the centering point?
No, that's what I'm talking about. Just in general, like if it's only at c where it converges,
Yep.
then that means that r has to equal 0.
Yep. And it could be at 0. It could be the centering point was 0, or centering point could have been 10.
Okay.
Or negative 9.
I was just trying to think in terms of
Like what would the number on the left be?
on this one, c
No.
equals 0, but r
C. Okay, centering point was 0.
centering point is 0, but r equals infinity.
Yep.
I was just thinking like,
If the radius is infinite, it really doesn't matter what the centering point was. Maybe that's what you're kind of getting at. Like, if your radius is infinite, whether it's centered at 0 or 10, doesn't really matter.
So is, in this case, because you're taking the limit and approaches infinity of basically 1 over n plus 1 times x?
Yep.
The
0 times x is 0.
And that limit approaches 0.
Yeah, because the limit only applies to n's, not x's.
Yes, so
Yeah.
it's basically 0 times x is less than 1, right?
Mhm.
So does that mean the radius, what is that?
I think, let's do another example, and I think you have a good point of comparison. I think you're trying to like discover everything through this one example. Let's do another one. I think you'll see maybe a point to compare. Check this out. Hey guys, let's do number 3. Number 3, same question, different details. So check this one out. What's the centering number? What's the C value for this power series? See it? It's positive 8, right? X minus 8 means centered at 8. So how far does this radius of convergence project out from that centering point? We're going to find out. So we do the same thing, limit as n heads towards infinity of, we don't need the alternating element, but it'd be x minus 8 to the n plus 1 over, this would be what, 3n plus 4? Yeah. 3n plus 4 times 3n plus 1 over x minus 8 to the n. We want that to be less than 1. Okay. So we do a little simplifying. What results from the x minus 8s? Sorry? Yeah, to the first? Yeah, okay. So it'd be x minus 8 to the first over 1 times, and it's 3n plus 1 over 3n plus 4. So as you apply the limit as n heads towards infinity, what happens with that? Hey guys, listen please. What happens with the expression with the n's? It's 3 over 3, right? Use the pre-calc trick. So you end up with absolute value of x minus 8 is less than 1. Right? X minus 8 is less than 1. So this is not 0 is less than 1, right? So let's think this over. I mean, there's a very simple way to do this, but let's think this over. What numbers would work for x to make this true? 9, because 9 minus 8 is 1. Anything bigger than 9, though, would be false, wouldn't it? Hold on. So 9 works. There's a lower bound, too. 9 and 7, right? Because what's 7 minus 8? And the absolute value of that is 1. So as long as we don't go past, as long as we don't go above 9 or below 7 or equal to them, we're good, right? Okay, so I would say this. Let's see if this makes sense to you. Radius, 1.
Whoa.
Check this out.
That was holy.
What's the centering point?
8.
What's the highest x value? If we go beyond it, we're in trouble.
7. Oh, 9.
What's the lowest? What's the distance from the centering point to the outer edge?
1.
Either way, it's 1. So what you can do, here's a way to find your radius. Once you've done your limit over here and simplified and done your limit and all that good stuff, if what remains has an x in it, then you can use that to help you calculate your radius. And we'll look at some more. We'll look at some other ones kind of like this. This one simply is 1, right? The biggest x could be is 9. The lowest it could be is 7. Centering point was 8. The distance between center and any of those would be 1 at most, right? Yeah.
Is that also the interval?
So this would give us, so that's where we're going to be heading next time. This would be the start of the interval of convergence, but we have to do, though, we have to decide, is it an open interval or a closed interval? So we got to fiddle around with the endpoints a little bit. And the good news is you're totally well equipped Like if you know what an alternating harmonic is, you're golden. If you know what a harmonic series is, you're golden. So we'll get there. Well, it'll be next time. But to get the interval, we need to figure out what's going on at the endpoints as well.
Bless you.
Bless you. Hey, good timing. Think we're in good shape. You guys are all free to go. Have a great rest of your day. What's up, Liz?
What does that look like if the radius is 1?
What does that look like if the radius is 1?
So, what happens outside of that radius? Even
Sure.
if you add like an infinite number of terms, like what happens?
In your calculator, will you put in, do you have your calculator with you?
Yeah.
Well, here, you know what? I might be able to do this real quick. Let me